Good morning, everyone, and welcome to the 2022 Virtual Viscosity Summit. We are so excited to have you all here and to start our year with this amazing panel of speakers. Speaking of our amazing panel of speakers, just to give you the agenda for today, at 9 a.m. right now, we're going to start with our speaker from Northwestern University. At 10 a.m., we'll have Kraft Heinz, followed by Carbon 3D. We will take a 1-hour break at 12 p.m. Pacific. And then coming back in the afternoon, we'll have the University of California, Santa Barbara, and we'll close out today with a speaker from RheoSense. We encourage you to follow us on LinkedIn, Twitter, and Facebook to stay connected with us and any of our speakers. And if you do have any questions, please ask them in the chat or questions panel. All of our speakers have set aside some time at the end of their presentations to answer your questions. And so we do encourage you to ask those along the way, and they will be answered at the end. Now, it is my honor to introduce our first speaker from today, Hammad Ali Faizi. He is a PhD in mechanical engineering at Northwestern University. His PhD research explores the mechanics of soft biological materials, from self-assembled cellular membranes to structured fluids such as surfactant-laden emulsions and viscoelastic liquid bridges. He's currently developing computational and experimental tools to study microscale physics and mechanical characteristics of these complex fluids. And today he's going to talk about fracture of viscoelastic bridges for dispensing applications. And without further ado, I'm going to pass it over to Hammad.
Okay, can you see my screen, Eden?
Yes, I can.
Hello?
Yes.
Okay, perfect. Okay, thank you so much, everyone. And thank you so much to RheoSense for inviting me. So here I will be presenting this topic, torsional fracture of viscoelastic liquid bridges. And here you can see this video where you would see dispensing. But what I want you to realize is that there are some dispensing problems in there. And we would go in a bit detail what we see over here and how we can tackle this problem. So going back to rheology, as we all know, rheology is study of deformation and flow of matter. And as you go from Newtonian fluids to non-Newtonian fluids, there are certain elements that start taking in. For example, the fluid can be shear thinning, where the viscosity would decrease. As you increase the shear rate, normal stresses would develop, for example, in shear stress flows. The idea of extensional thickening would occur. And this is something where I would go in more detail in this talk. And then you see materials with both solid and fluid kind of properties, which are known as more of the viscoelastic materials. And these kinds of behavior basically starts affecting many of your industrial applications. For example, in spring and atomization, where you can see this jet coming out, but with a lot of stringiness, as you can see, or even in coating technology. And this is because just of the added constituents or rheological modifiers, for example, polymers, particles, surfactants that can lead to stretching and stringiness. And in particular, I'm super interested in the idea of dispensing. And the first encounter that you see in dispensing is whenever you are, for example, dispensing out your food product, for example, any sauce, ketchup. So whenever you use the container and you push on it, the ketchup or any sauce would come out from it. And this is the first idea of dispensing. Now, when you go to some industry, for example, in inkjet printing, you also see this phenomena of dispensing where you have a nozzle head where the fluid would dispense out either in droplets or coming out in jet. So as we are more aware and we encounter printing every day, so it's a very good problem to first pick it up and go from there. And in inkjet printing, there are a lot of problems. So the goal whenever you are doing inkjet printing is that you want small controlled droplets with very high productivity and extreme reproducibility as well. Now, you also want to dispense different kinds of complex materials for whatever application you are needing for. And if you look at this nice cartoon that is from a very recent review paper from Detlef Lohe's paper, you can see that there are 7 kind of fluid dynamics rheology problems that are going on that one needs to tackle and one needs to take care of. First, you have this fluid that is coming out from this Inject printhead. And then once you have to first push this fluid from the printhead. And then there's a problem of the bubble entrainment, which is the second part labeled. Then you also have to take care of the wetting dynamics that comes out from the nozzle. And then comes the dispensing part where you have this jet that comes out or dispense droplets. And then you need to take care of how it would kind of impact the substrate and how, for example, the drop film interaction would take place and how evaporation would take place. So you can see that it's a multidimensional problem. And here we would just focus on just the dispensing of these droplets and jets and how we can basically tackle this part to make our dispensing more efficient. Now, if you just look at Newtonian fluids, the simplest of the fluids, what you can do is you can kind of characterize this into dimensionless numbers. One is the Ohnesorge number that represents material properties of the ink, for example, which is basically the ratio between viscosity and capillary timescales. And if you look at the Reynolds number, which basically is representing inertial forces with viscous forces, and in the Inject problem, it represents the inject velocity and the pressure that builds up in the ink chamber. You can create this nice diagram where you can see that you have a very small sweet spot where you have to control the Ohnesorge number and the Reynolds number to basically dispense out your material properly. If you're not in this range, you can have a lot of problems. For example, if you have a very low Ohnesorge and Reynolds number, you can have insufficient energy just to pump out that fluid from the dispenser head. Or if you have a lot of inertial forces, there are problems that there can be satellite drop formation or onset of splashing. Or if it's a very high Ohnesorge number, it can be too viscous for the fluid to dispense out. So you can see a very sweet spot of dispensing in this regime of this diagram. Now, this is just for a Newtonian fluid, mind you. What if you have a non-Newtonian fluid as well now? So the problem gets more complicated over here because, as I discussed, there are more of these other material properties that start sticking in. And this is the problem that is very recurring, for example, in electronic packaging, where I have this nice video where you can see that there is this dispenser head nozzle. It makes a complex pattern on a PCB circuit board or a silicon die. And after this pattern is made, the nozzle would try to retract up. But what you see over here, first of all, you see this long tail coming out. Not only that, but this long tail or this dispense part takes a considerable amount of time to dispense as well. And if you have more inertial forces, for example, you also have this problem of satellite drop formation. And in rheology, this is more known as stringiness or tailing issues that form with these viscoelastic fluids. And basically, this is because of extensional hardening of this viscoelastic adhesive that happens in, for example, in this die bonding application. Now, this is not only in electronic packaging, but it's also, for example, in additive manufacturing. For example, here you can see that you have this 3D printed part. And if you're not working with it the right protocol or regime, you can have these strings that are forming, for example, in this 3D printed part as well. Now, in essence, what you would want would be this nice dispense pattern. But because of this issue, for example, of stringiness, where the tails can kind of contaminate the neighboring dispense part, you can have a bit of an issue over here. So what is happening over here? So basically, this is known as more of the extensional viscosity problems, where it's very analogous, for example, to a rubber band, or just consider that you have a blob of fluid. It's a polymeric fluid. Now, as you try to stretch that blob of fluid, you have these polymer chains that start aligning, and they kind of resist your extensional stress or the tensile stress that you are trying to give. And this is very analogous to a rubber band. If you're trying to pull the rubber band, the rubber band would get a bit more harder to stretch. And this is where you feel that extensional viscosity that kicks in. And more in the definition form, it's the resistance to extensional stresses given by the normal stress difference divided by the extensional rate. And as I said, It's pretty recurring in printing industry or additive manufacturing, for example. Now, as you saw in that video, what is happening over here is that first, whenever the dispenser comes to the substrate, it forms that liquid bridge. Now, because capillarity would not allow this bridge to break up, so the idea that is used currently in industries are that the nozzle would simply retract up and it would allow to go under an instability, which is beautifully given in this instability diagram, which is given by the volume of the fluid, the aspect ratio given by lambda, and the bond number. So for example, if you're changing the aspect ratio, which is the length of that bridge divided by the radius, you can increase the length and then it would go under a bifurcation instability, or the bridge would just go something similar to a radial plateau instability and the bridge would break up. Now, this instability diagram is also dependent on the bond number, which depends on the gravitational forces given by rho g r squared and the surface tension. And as you increase the bond number, the gravity would also play a role on your liquid bridge that you're forming, and this instability diagram would shrink. So the first idea is that first you want to make the bridge unstable, and then the bridge that formed would start thinning. So the radius that you have, this 2r, it would start thinning. And then what happens is that now you have capillarity that is trying to break up the bridge, and you have viscosity, inertia, elasticity that is kind of resisting the bridge breakup now. So you can see that rheological effects starts complicating. And if you have a Newtonian fluid, you would just care about viscosity and inertia. However, as most of the fluids in industries, for example, are non-Newtonian, elasticity also becomes a huge part in that. And you can capture these ideas in, for example, in Ohnesor's number, which is again viscosity divided by inertia and capillarity, the elastocapillary number, which takes elasticity and capillarity divided by viscosity, and then the Deborah number, which takes account to elasticity, capillarity, and the inertial forces as well. So these numbers basically summarizes the material properties that would govern, for example, this liquid bridge breakup. Now, these are the material property numbers. You also have to consider the dynamic property that when you are forming the jet, when you are forming the droplets, whenever you are dispensing or making this bridge, and this is beautifully captured in this map of misery that comes out from the paper from Classine, which kind of tells you in what regime you would be working at, or for example, whatever material properties you have and whatever kind of dynamical numbers you apply, what kind of phenomena you would expect. Whatever you do, you're still not able to tackle that extensional problem that I was showing you, where you would have the strings that would be forming and long breakup time. Now, coming back to that part, it's not always the case that you want to always break that bridge and you want to get rid of it. Actually, in rheology, these kind of setups are pretty useful. For example, to also measure extensional properties. For example, you have this famous table rheology rheometry, where what you can do is you can form these bridges and you can also backtrack to know more about extensional properties, or for example, relaxation rate. And there's a recent technology known as stripping on the substrate rheometry, which is even faster for smaller relaxation times. So on one end, you want to break up these bridges, but on the other end, this is also useful to know more about extensional properties as well. And over here, you can see different kinds of fluids on how you would expect radial thinning to be happening. For example, in a Newtonian fluid, in a non-Newtonian shear thinning fluid, or in viscoelastic fluids. So going back, if I look at a fluid, and a very well-known fluid, for example, a Boger fluid, which has a very high viscosity and a very high elasticity as well, you can see that if I see the thinning of this bridge, whenever I do dispensing of it, first this bridge would go under the effects of viscosity and capillarity. And as the bridge would start thinning up, you would have extensional viscosity playing a role, you would have the polymeric chains aligning up, and then elasticity would start playing a role as well. And you can see that it almost takes 200 seconds for these kind of bridges to break up. Now, there are methods that have been tried and implemented in order to help with these kind of problems. For example, what you can do, you can introduce bubbles, for example, in these liquid bridges, and you can take the bubble pop up in order to help with the dispensing, or you can modify electrical properties of the nozzle or the substrate in order to help with the dispensing. And these are some of the other ideas I was involved in when I was working at ASM in order to help with this dispensing, where you can see what you can do is you can add a vibrating coil to the nozzle head, and maybe you can help with the instability, or you can have a different motion profile in order, again, to help the instability to go up faster. However, you can again see that these tails are still forming. It's taking a considerable amount of time for these bridges to break up. And at that point, I literally wished I had magical scissors to cut these fluids cleanly, because the problem is that the dispensers themselves are pretty sophisticated. So I cannot add a very sophisticated mechanism to help my bridge break up as well. I have to work with something very clean and something very easy to implement. So we were thinking more about the tension forces that we can apply on these liquid bridges. How about if we apply torsional forces as well? Can I somehow use the centrifugal forces and change the interaction of inertia, elastic, viscous, and capillary forces? So what if I take a viscoelastic grid and I apply torsion, can this help me with this problem as well? So let's think about this problem now. So the goal is that I want to design a simple engineering solution to improve the dispensing of these viscoelastic fluids, and then use rheology to understand the solution so I can translate to other kind of problems and other kind of fluids as well now. So here's the experimental setup where you have this motor connected to a liquid bridge, and this the lower cylinder is retractable, so it can go up and down. So you have this motor that you can apply rotational forces. And the two fluids that I would like to compare would be infinium, which is a Newtonian fluid that would study viscosity and capillarity. And mind you, the viscosity of this fluid, infinium, is 30,000 times that of water. So you can see that how much viscous fluids we are playing with. And the viscoelastic fluid that I would like to compare would be silicon oil, which would compare viscosity, capillarity, and elastic effects as well. So we would try to model our silicon oil with the 3-mode e-Sickes model. And in a bit, I would let you know why this model would be very useful. And one can use time temperature superposition in order to use that to get out material properties. For example, the mobility parameter alpha, the average viscosity, the relaxation times as well. And then you can see whether you have a nice parameters that you get out from your fitting, and then you can compare with the differences between the first normal stress difference and the second normal stress difference, and then the first normal stress difference as well, using rotational rheometry. And you can see that you have a very nice collapse of the model that you use and the experimental data. Now let's warm up. Let's first go with the easiest case, and let's just go with a Newtonian fluid. And let's see what happens when you have a Newtonian fluid when you don't apply any centrifugal forces. So you have a Newtonian bridge that you form, and it has different aspect ratios. The volume of the fluid is the same. What we are doing over here, we are using different aspect ratios. So when you have a thick liquid bridge or with a small aspect ratio, for example, 4.5 millimeter, you can see that the fluid radius would decrease. So it would first go with a gravitational drainage above this bond number of 0.025. And then what would happen is that as the bridge would start becoming thinner, it would have this effects of competition between viscosity and capillarity. Now, as you increase the aspect ratio, you can see that now viscosity and capillarity would only be the two forces that would determine the effects on the bridge thinning. And in terms of the velocity fields or velocity development fields, you would only have VZ that would be forming. So this is a liquid bridge breakup of Newtonian fluids without any centrifugal forces. Now, when you add centrifugal forces, so over here you can see that first of all, the bridge would start. So you have the same bridge that I was talking about, the one that breaks up the slowest, the 4.5 millimeter one. So it was taking 60 seconds. Now, if you start applying rotational forces, centrifugal forces, or you increase the rotational rate, you can see that the bridge is breaking up faster. And it almost improves by 9 to 10 seconds. But what is the most important thing that we realize from this setup is that with this setup, what we find is that the bridge actually breaks up like a rotational body rotation. So what you see from this v theta velocity or the angular velocity, that at the center, the velocity is 0, but towards the surface, you have the highest velocity, only at the upper bridge part. So what you are seeing is that the lower bridge is not moving. The upper bridge is moving, where the velocity profile increases linearly from the center towards the surface. And so this is a solid body rotation, and you have concentration of shear stresses at these necks. So you have the solid body rotation going on, and you have this concentration of shear stresses. And once again, that the formation of these bridges are more like pancake shapes, or as you can see from these diagrams. So what we find is that centrifugal forces would help to spread outward in the radial direction and in a pancake shape. Now the dispensing would improve from 60 seconds to 9 seconds. And what we see is that the solid body rotation leads to concentration of shear stresses at these local curvatures. Okay, so going from 60 seconds to 9 seconds, okay, it's a good improvement. But can we expect something better? Because we want to now dispense very tough fluids, and maybe 9 seconds is not the best number that one would want, maybe. So let's try to go and let's try to see what can happen with a viscoelastic fluid now. And here's a viscoelastic bridge that is formed between the cylinder and the nozzle head, and this bridge would never break up. So it's stable under capillarity. So if you leave it as like that, so under capillarity, this bridge would never break up. But let's see what happens when I apply a rotational stress over here. So this video is 20 times slower, and the maximum shear rate that is applied on the curvature is around 1,000 inverse seconds. So you have these localized shear stresses, and you would start seeing that there would be an indentation that would form on this viscoelastic bridge, and this indentation would propagate towards the center, trying to cleanly break up this fluid. So an indentation forms at the surface, and it cleanly propagates toward the center to break the fluids. And if I try to visualize this video now 2 times slower, you can see that a bridge that would never break up, a viscoelastic bridge, can be broken within less than a second now, through this beautiful crack propagation that eliminates stringiness. The breakup time reduces considerably, and you have no satellite drop formation that is forming over here. So let's try to see now what is going on, and if somehow we can understand this and try to more imply for more kind of applications as well. So here is this viscoelastic case that we were seeing. So first of all, what I want you to realize that the crack that forms, that indents that were forming, were smaller than the capillary length. So that means that gravity is not playing a role. So you can see the size of this crack that forms is given by this length A, is smaller than the capillary length, which means that gravity is not playing a role over here. Second of all, there are emergences of normal stresses, because you can understand that from the Gieseckers model. So I was telling you that there are these localized shear stresses that would develop just because it's a solid body rotation. Now there's a positive feedback, because shear stresses would lead to normal stresses as well, the first normal stress difference and the second normal stress difference. So you can see that because of the shear stresses in viscoelastic fluids, you have development of normal stresses as well that would happen. Now, if you look at the radial profile thinning in this diagram on your right, you can see that whenever I have a viscoelastic liquid bridge, it would never break up, as I showed you in the video, when you do not apply any torsion forces. However, as you start increasing your torsional forces or rotational rates, you can see that the radial profile thinning is given by this power law, which is dependent on this beta parameter. So as you increase the rotational rate, the radius decay is faster, and it just depends on this beta parameter, which is showing a power law effect. So, so here you can see that these square ones are the experiments, and the solid lines are from the simulations. So what you can do is you can change this viscoelastic simulation into a Newtonian fluid case as well. And you see that when you apply torsional force to this kind of a setup, to this Newtonian fluid, it would not break up, because as I said, it would be just stable under capillarity. And when you apply that torsional forces, it's just that these indentations that were forming in the viscoelastic bridges do not form in Newtonian fluids. That means that it is a normal stress effect that is causing these kinds of indentations to form now. So now the next question I want to ask is if the stress is a first normal stress difference effect or a second normal stress difference effect. Which stress is forming this indentation propagation? And is there a dimensionless number that can help me control the breakup? So if I just can calculate a dimensionless number, can I expect what to happen? So for that, what we can do is we can use dimensionless analysis, and we can recast the Reynolds number, the Weisenberg number, which takes account of the elastic effects with viscosity, and the Capillary number, which takes account of viscous effects with the Capillary effects. So you can see that if I plug and chug the numbers of my material properties and the dynamic properties, I can calculate the Reynolds number, the Weisenberg number, and the Capillary number. So one can see that the Reynolds number is pretty small. So we can ignore the effects of the Reynolds number. And you can see now we have two numbers left. That is the Weisenberg number and the Capillary number. But the problem in Weisenberg number and Capillary number representation is that the rotational forces, or this omega, which is the rotational rate that you apply, is there in both. So we don't know how this is playing a role. So what we can do is we can recast the Weisenberg number and Capillary number in two different numbers, which is the elastocapillary number and the Tanner number. So elastocapillary number takes account of the elasticity with viscosity and capillarity, and Tanner number is a new number that we have coined, which takes account of the normal stress difference that form with capillarity. So you can see that the elastocapillary number is pretty small. So we can say that this effect is the effects of the normal stress differences and the capillarity, or the Laplace pressure. But at this point, we are still not sure if it's the first normal stress difference or the second normal stress difference given by these parameters C1 and Phi2. So one can go in more detail to see what happens. So what we see over actually here is this edge fracture instability, and this instability was first discovered by Professor Roger Tanners in Sydney, and that's why we gave him the honors by coining that number, because he was the first one to discover edge fracture. And this is something that you observe in your rheometer, in your rotational rheometer. So here you can see this first image that of this edge fracture, and you have these fluids inside your rheometer, and you can see that as you apply high rotational rate, you would have these indents that would form. And then what happens is that as you apply higher shear rates, that this material can leak out. So this is a phenomena that you really do not want to encounter in your rheometry measurement. And what is happening over here, there's a criteria that the second normal stress difference should be much higher than the Laplace pressure. So this is a criteria we satisfy in our problem as well. Now, what you can really do in order to confirm whether it's a first normal stress difference or the second normal stress difference is that you can use this mobility parameter from your simulations. So the mobility parameter basically changes the first normal stress difference effects and the second normal stress difference effects. So as you increase the mobility parameter alpha, going from 0.15 to 0.49, you can see that the second normal stress difference increases and the first normal stress difference decreases. And what I want you to concentrate would be on the 0.6 seconds. And you can see that as I'm increasing the mobility parameter, the indentation propagation is much faster as the mobility parameter is increasing, or the magnitude of the second normal stress difference is increasing as well. So you can see a direct correlation between the increases in the second normal stress difference and the propagation of the indentation. So we kind of get the idea that it is maybe it's the second normal stress difference that is causing all these effects. So the Tanner number that we coined, and at that point we were not sure whether it's the first normal stress difference or the second normal stress difference, now tells us that it's actually the ratio between the second normal stress difference and the capillary stresses that form. So one can do an experimental verification as well. So I told you about that beta parameter, that power law parameter, and I can plot that for different kinds of silicone oil with different kinds of viscosity, different kinds of relaxation rates. And you can see when I plot this beta parameter, it kind of has a dispersed relationship between beta and the rotational rate. However, what I can do is I can recast the same data with the Tanner number, and you can see it's a perfect collapse, which tells you that the breakup is exactly governed by the Tanner number. Now, you can use simulations as well to learn more about the Tanner number, and you can see that there is such similarity between the breakup. So if the Tanner number is the same, so in this simulation, what we are doing is we are changing the viscosity and the surface tension. So you see that as far as the ratio of the surface tension and viscosity remains to be the same, the bridge would decay with the same profile, or it would exactly decay alike. However, if the ratio changes, for example, now you have a higher viscosity, a higher surface tension given by, for example, this black solid line, you can see that capillarity would arrest the indentation. However, as you decrease the surface tension or you increase the viscosity, which means you're increasing the second normal stress difference, as it's a positive feedback, you would see that the bridge would break up then. So what we learned is that there's similarity in the indentation shape and the stress fields as well. And if you apply a high rotational rate to the diagram on the right now, you can see that the higher rotational rate also means that the second normal stress difference propagation is much faster, and the bridge would again break up much faster now. So in summary, what we have learned is that edge fracture that is actually not wanted in rheology, or sometimes as rheologists, whenever you are doing rotational rheometry, we would want to avoid it, can be used for as an advantage, or can be used for useful purposing to destabilize viscoelastic liquid bridges, for example, in dispensing problems. And over here, I complete that that image when I was showing you towards the introduction, that you form that liquid bridge. Now, what the industry is doing right now is trying to retract this liquid bridge by forming, by taking that instability and letting the bridge to thin down. But what we are proposing is that instead of retracting the nozzle, let the nozzle be at the plate and rotate, because you would develop edge fracture that would help you to destabilize. And we also saw that the indentation propagation is just governed by this very nice dimensionless number, which is the Tanner number, that can give you much information whether you would expect a breakup to happen or not. And there are a lot of remaining questions. First of all, why do we see that similarity solutions? What can be analytical approaches to this kind of a problem? And what if you have an elastic capillary number which is much higher than 1 now? And what would you expect, for example, with yield stress materials? So here I would like to acknowledge Okinawa Institute of Technology and Eindhoven, with whom I was working both on the experimental part and the simulation part. And this paper is published, so you can go and check it out and let me know if you have any questions. And with that, I would want to thank you for listening to me, and I'm open to any questions now.
If anyone has questions for Hammad, again, please drop them in the questions panel or in the chat panel. And Hammad, we will give everyone just 1 minute to drop their questions in.
Mm-hmm.
So we have our first question, and it is there a way to predict through rheological tests the degree of satellite droplet formation?
I think, yeah, there are little studies that has like kind of predicted how satellite drop formation would take place whenever, for example, you are jetting. And this is just because the Rayleigh pattern instability, and there are a lot of studies from groups from that Lohes, Osman Bazran. So basically, it's the inertial effects that start kicking in, and that would start changing from going from just the strings that you form with satellites as well. So yeah, so it's more of the inertial play that would come more with the capillary effects that would start forming these satellite drops.
And again, for all attendees, if you do have any questions about any parts of the presentation, please just drop them in that questions panel. As Hammad has left some time. So we do have a question, and this is a bit for us, but a bit for you as well, Hammad, is could we download the presentation? So the recordings from today will be shared with all of our attendees. Sharing the actual presentations will be something that's dependent on our speakers, and they will be shared with the recordings if available. So the recording will be there, but a download of the presentation will only be there for the speakers who are able to provide that for us.
Sure, you can reach me out. I can give you my email address, or you can connect me on LinkedIn, and I can definitely share my presentation with you if you're interested in that.
Perfect. Yay, more are coming in. Is there a way to predict the shear rate at which edge fracture begins, considering the rheological properties of the fluid?
That's a good question. So one way that you can always, that's how we were predicting, was that our experiments and simulations were matching. So when that starts happening phenomenologically, you can start using your simulations to predict how much shear rate you should have. So for example, as I was showing you in the, let me see if my, as I was showing you the video, for some reason my video, my presentation, I'm trying. Okay, perfect. So as I was showing you that video, you can see that here we have predicted the shear rate, which is 1000 inverse seconds over here. So one way that, as I mentioned, you can do it by comparing your simulations and experiments, and you can use simulations to predict that. The other way that we also tried was, and that gave a very good number, was kind of do a PIV on this, or a PTV, where what you can do is you can have these particles that you can attach to your bridge, and then use high-speed imaging to kind of measure what you can expect from there. So yeah, there are ways to get around with it.
Hammad, is there a rheometer that you recommend or one you used?
So for the rheometer, what we have done over here, so for example, in this one, the measurements that we have done over here, we have used an Aries one in order to do our rheometry. So I wouldn't say that I have a recommendation. I had good, kind of, so there are always advantages and disadvantages of what kind of rheometer you are looking into and what kind of applications you have. So it really depends on that. So I wouldn't give you a specific answer unless and until I know what kind of applications you are looking into. So if you can let me know more about what kind of application, then maybe I can give you a much better answer. But over here, for example, in our experiments, we have used an Aries rheometer. So yeah.
Wonderful. And some people are asking to connect with you, Hammad. And is it okay if I share your LinkedIn page with all of our attendees, the link to it in the chat?
For sure, for sure. I would be very happy to take questions over there and connect with you in future so we can talk more about science and industry.
So for those looking to connect, I am going to send in our questions panel a link to Hammad's LinkedIn so that you're able to connect with him directly and continue any conversations you have about dispensing and viscoelastic fluids and the research that he's doing. And we can give it just one more minute, Hammad, before we wrap up to see if anyone else has any questions that they'd like to drop in. They have been coming through, so I want to make sure we address everyone's questions. All right, well, it looks like we don't have any more questions. If anyone does have questions, again, you can connect with Hammad via his LinkedIn. We shared that link directly in that chat panel. And I would like to say thank you so much to you, Hammad, for sharing this with us and for speaking at the summit. It's been such a pleasure. And
thank you so much.
Look forward to seeing,
it was my pleasure.
We look forward to seeing additional work that you do.
Thank you. Okay.